and today we're going to be deriving the wave equation and also considering boundary conditions for it. So let's get into it. So first, we're going to draw a wave so that we can kind of understand what forces are acting on it. So let's say we have this portion of a wave from here to here, right? So we'll call this x, and then we'll call this x plus change in x. Next, we will draw the free body diagram for this and what forces act on it. So in this case, there are two forces acting. One in this direction with an angle of theta. Theta, we'll call it at x comma t. And we'll call this force t of x comma theta, comma t. And then we have another force here, which is acting at an angle of, call it theta x plus change in x, comma t. And the force is a tension force, t of x plus change in x, comma t. Now, using Newton's second law, we can write F equals ma, and we can describe what's occurring as now a partial differential equation, where F is, and here what we want to do is we want to create a partial differential equation for, I should mention, a partial differential equation for the y position, which we'll call u. We want to create an equation for u x comma t based on the parameters of x and the parameters of time, right? Based on where we are and at what time we are. We want to know what our vertical position is since we're deriving the one-dimensional wave equation. So F equals ma. Well, we know our force, since we're just trying to describe the force in the y position, we can describe it as t sub y of x plus change in x, comma t, minus t sub y of x comma t equals some kind of mass times partial squared u, the second derivative of our y position with respect to t. Now, mass can be rewritten as whatever the mass density is, we'll call it rho naught, times the length of the string, which we'll call change in x. Then, and t sub y can be described using trigonometry, and we can say that it's just the tension force times sine of that angle, theta. Then we can rewrite our equation, because we know what theta and t are, and now we know what mass is, as tension at x plus change in x, comma t, times sine of theta at x plus change in x, comma t, minus t at x comma t, theta at x comma t, and that is equal to rho naught times change in x times, again, the second time derivative of the y position. Now, we can divide both sides by change in x, giving us, let's see, divide change in x, divide this side by change in x, and you'll notice that what we have here looks quite a bit like the limit definition of a derivative. And in fact, when change in x is really, really small, it becomes the derivative with respect to x of t at x comma t sine theta at x comma t. Equals, again, rho naught gradient squared u over gradient t, partial squared u over partial t squared. And now what we can do is we'll use a trigonometric approximation called the small angle theorem, where sine theta is at very small angles. Sine theta at small angles, sine theta is approximately equal to tan theta. If you want some intuition for this, you can think of it, you could think of it visually. So if you look at the graph of tan theta, one second. If you look at the graph of tangent theta, it looks something like this. And if you look at the graph of a sine wave, it looks kind of like this. So you could see how very close to the origin at small angles, they follow a similar trend. But also another way to think about it is tan theta equals sine theta over cosine theta. And at very small angles, very close to 0, cosine theta is around 1. So then tan theta is around sine theta. And tan theta, because it's the slope, dy over dx, or in this case, gradient u, the y position, divided by gradient x, the x position. And so you can rewrite this equation now as gradient over gradient x of, call it t naught, because we'll assume that the tensile force throughout the string is more or less constant, times gradient u over gradient x equals this rho naught gradient squared gradient over gradient t squared. Whoops. And the t naught we can carry outside because we're going to assume it's a constant, and we can divide both sides by p naught, giving us gradient squared u over gradient x squared times c squared is equal to gradient squared u over gradient t squared, where c squared is equal to t naught over rho naught. If you want some intuition as to why it's c squared, look at the units. So the units for t naught, because it's a force, is kilogram meters per second squared. And the units for p naught, which is the mass density, is kilograms per meters. And so what you'll notice is the kilograms cancel and the meters multiply with each other, giving us meters squared per second squared. And so, in fact, this c value has some is related, or is a fundamental parameter to this wave. It's like a fundamental speed to this wave, which we'll understand more the physical interpretation of once we solve this equation. But for now, this is the derivation of the partial differential equation for the wave equation. You'll notice the only difference this has with the heat equation is that we're looking at the second derivative with respect to u rather than the first derivative, or with respect to t rather than the first derivative. And so the way to solve this equation is actually quite similar in ways using separation of variable and Fourier series, very similar to the heat equation. Now that we've derived the equation, we also need to look at boundary conditions. And boundary conditions, again, are also pretty similar to the heat equation in that there are three of them that we can look at. First, prescribed boundary conditions, which is simply put where prescribed boundary conditions, which is just where we say that the boundary condition at u of 0, t equals some value, say 0, and at L, t equals some value, say also 0. And so this is also called, it's called prescribed boundary condition, but also we can call it a fixed ends. And to visualize what this would look like, you can think of a wave which goes up and down, going through like all the different phases, but the ends being fixed. And this is very similar to the heat equation with prescribed boundary conditions. We can also look at what I call like insulated boundary conditions, or free ends, which is that if you wanted, for example, one of these ends to be free to move around, so that when you wiggle it, it just follows whatever the tensile force at the end of the string is. All you have to do is you say that the derivative at, say, L, t is equal to 0. And I should also mention the fixed end can be constant for fixed end, but the prescribed boundary condition can also be a function. So say, for example, you yourself are moving the wave back and forth, up and down. Well, you can describe the way that you're moving it. So let's say you're here, you're here moving the rope up and down, waving it up and down. You can describe that as a function f of t, and then that can be your prescribed boundary condition instead of just a fixed end. And then finally, also pretty similar to the heat equation, we can have our boundary condition be described by a dynamical system, right? By a dynamical system. So let's say, for example, our boundary condition are one of the ends of our wires, or one of the ends of our rope is connected to a spring, right? Like this. Well, then the way that this boundary condition at u of 0, t, it follows some function y, which can be described by an ordinary differential equation, Hooke's law, the ordinary differential equation, which is Hooke's law, which can be written as md squared y over dt squared equals minus Hooke's constant times y of t divided by, or minus whatever friction force occurs, y of s, minus whatever the equilibrium position is, L, plus any other forces. And in this case, that other force is the tensile force that we're dealing with, right? And so then this ordinary differential equation can be rewritten as d squared dt squared of u at 0 comma t equals minus k times u at 0 comma t minus y sub s minus L plus T naught times partial or du over dx of 0 comma t. And if you solve this ordinary differential equation, you will be able to get the initial boundary condition, which is represented as like a spring on a mass on a spring.